Well, we are just flying through these concepts in derivatives, and tonight's lesson is all about concavity. So I'm hoping you've heard that word before, and we'll explore a little more about it tonight. So what do we mean when we say concavity? Well, first of all, I want you to get the terms in your notebook. Concave up. And a concave up function looks like this. What this implies is that the first derivative is increasing. So again, pause and get these in your notebook. Now, what do I mean when I say the first derivative? Well, remember, derivative is another word for slope. What it's really saying is the slope is increasing. So let's think about this. If I had to put little tangent lines on there, all right, I would say that's definitely very negative, maybe like a -8. And as I continue down, I get less negative, maybe that's a -2, until I get to here, which is a 0 slope. So notice, if I go from a very negative to 0, that means I'm increasing. If I kept going and assigning numbers, maybe a 1, maybe a 5 at that tangent line, you can see that the slopes, or the first derivative, is increasing. Therefore, that implies the second derivative is positive. So a little rhyme, I guess, is concave up is shaped like a cup. You can think of it as smiling for up. And that, remember, that implies the second derivative is positive. So you can kind of make a nice little happy face out of that to help you remember. Concave down, then, looks like this. And let's get this in our notebook. The first derivative is decreasing. So again, if I had to assign slopes, remember the first derivative is just another word for slope. Again, if I had to put little slopes, little tangent lines on there, this is very positive, maybe a 5. But then it gets smaller, maybe a 3, a 2, until I get to here a 0. Now I'm getting negative, and I'm getting more negative. Maybe that's a -1, but this is a -6. All right, so you can see that I started positive, but I got smaller. So the first derivative is decreasing, and the second derivative then is negative. And so you could put maybe some negative eyes there, make it look really frowning. So concave down like a frown to help you remember that one. Lastly, we should all know, obviously, like a linear function. It's just a nice straight line. The first derivative is constant, and of course what I mean by that is the slope is constant. Now I didn't certainly have to make it 0. Let me make a positive slope there. Maybe this whole line has a slope of 2. This line had a slope of 0. Either way, it's a constant slope. The slopes aren't changing. No matter where I put my tangent line, I'm going to get the same slope. Therefore, its second derivative is 0. The next thing I want to talk about is just take a, get a nice sketch of your sine curve in there, and let's talk about points of inflection. Okay, another way to say this is inflection points. This can be abbreviated as POI. The AP is perfectly okay with that. Or again, inflection points. Now, what an inflection point is where the graph changes concavity. All right, so I think as you look at this sine graph, you can clearly see that there are different concavities here. As I start off, would you say this section is up like a cup or frowning? Down like a frown? Well, I would say it's frowning, and then someplace, all of a sudden it magically changes, and now it's concave up like a cup. So where that point turns, where I turn from concave down to concave up, okay, that's called an inflection point. And I would say that's happening maybe right around here. All right, so I'm going to label that as a POI. I have a point of inflection. And again, if you were to basically cover this section up with your hand so it wasn't there, okay, if you pretend this isn't here, put your hand on top of it, and you only look at this section, you would say that's concave down. Now if you covered up this section like it wasn't there and you started here, you would say it's concave up. So where it changes is called that point of inflection. Now I think you'll see at least 2 more. Notice you're up like a cup, and then all of a sudden you're down like a frown. Where that changed, maybe right around here, is another POI, a point of inflection. And I think, again, it's going to happen down like a frown, and then you can see that it's starting to bend up like a cup. So it's definitely having another point of inflection here. Okay? And these points of inflection happen when the concavity changes or when the second derivative changes signs. So first example, state the intervals, and notice it's plural, on which the graph of the function is concave up, concave down, and state any points of inflection. All right, so what should give it away are the words concave up, concave down, points of inflection. And in your head, siren should be going off, and you should be saying all of that refers to the second derivative. All right, so we just have to take our time. We'll take the first derivative, then we'll take the second. So let's start with f prime of x. I'm going to get 12x minus 4x cubed. Okay, now again, these terms all refer to the second, so now take the second derivative. I get 12 minus 12x squared. Okay, that is what I'm setting equal to 0 and solving for. So I can pull out a GCF of 12, and I get 1 minus x squared. I can tee it up, so I get 12 equals 0, which is nothing. I can say this is really 1 plus x and 1 minus x, so I get x equals plus and minus 1. Notice I only had an x squared, so I should only be getting 2 answers. Now here's where we have to be careful. Notice all of those were the second derivative. So when I make my sign chart, I'm labeling it f double prime. Okay, and it's describing the function f. The reason I'm using is f double prime, I'm looking at the second derivative, but I'm still describing the function f. My only critical points were plus and minus 1, so those go on there. And again, I'm just going to put a 0. That's when my derivative actually equaled 0. It did exist. It had a slope of 0. And I'm going to test some points. So here I'm going to test negative 2, 0, and positive 2. Now recall that I'm plugging those into the second derivative, and that's what it tells you here. So I'm just going to kind of box in my second. I like the factored version. I'm boxing in my second derivative, and remember, I just care whether it's positive or negative. I don't actually care what the value is. So when I plug in my 2, I get 1 minus 2 squared. 1 minus 4 is clearly a negative number. When I plug in 0, 1 minus 0 is a positive number. And when I plug in negative 2, I get 1 minus 4, which is a negative number. Now notice, I'm not going to draw these arrows for increasing or decreasing because that's not what the second derivative describes. The second derivative describes concavity. So I am literally going to draw a concave down frown, concave up like a cup, concave down frown here. And now I can answer several questions. First of all, let's talk about our concavity. You are free to abbreviate CCU for concave up, and I would say this function is concave up between negative 1 and 1, and my justification, the part that's going to get me my credit, is f double prime is positive or greater than 0. That's probably the easier way to say it. I am concave down on 2 intervals from negative infinity to negative 1, and 1 to infinity. Okay, you can kind of just put the word and there or a comma. And my justification, of course, is f double prime is negative or less than 0. Now, do I have a point of inflection? All right, and again, you can abbreviate that as POI as well. A point of inflection occurs if f double prime changes signs. Look at this f double prime row. Did you change signs? Well, negative to positive, so there's 1. Positive to negative, so there's a second one. So I would say I have 2 points of inflections at x equals positive and negative 1. Now I don't have to be specific whether I went from positive to negative or negative to positive. All I need to say is f double prime changed signs. And there you have it. So using the second derivative to describe the concavity or the shape of our graph. Next question. Consider a differentiable function f with a given first derivative. Find the x-coordinate of any inflection points and then state the intervals on which f is concave up and concave down. So again, the keywords that should be jumping out of the page at you are concavity, and in your head you have to be saying, I need the second derivative. Okay, so lots of self-talk. Concavity, points of inflection, second derivative. Now, what's really generous, first of all, they tell you it's differentiable, which means you can take the derivative, and they gave you the first derivative. So they did half the work for you. All you need is the second derivative. Okay, so when I read that out loud, it says x squared times this quantity. So I'm going first derivative of the second plus the second derivative of the first. Okay, the derivative of the first is pretty straightforward. I'm going to say a 2x there. I'm going to slow down on my first derivative here. So I'm going to say that's 3, keep the inside, raised to the second, times the derivative of the inside. Okay, now your calculus is actually done. The rest is just factoring, which we've done for years, and plugging numbers in. So as I look at my GCF, remember we're always pulling that out, I'm going to take out the smaller quantity, so I'm going to take out an x squared minus 4 squared. And it looks like I can also take out a 2x, so I'm going to take out a 2x with that. Okay, so I'm just looking at this first set and saying, well, what's left? If I took out a 2x and an x squared minus 4 squared, I look like I have 3x squared. Then I've got a plus sign. I took out this 2x and I took out this squared, so I'm left with one of those, x squared minus 4. So as I rewrite this, I've got 2x, the quantity x squared minus 4 squared, and that's 4x squared minus 4. Okay, so as I clean this up, I'm setting that second derivative equal to 0. I'm teeing up all the different sections that I have. So this one's going to say 2x equals 0, so I know I get x equals 0 as an answer. Let's see, if I factor this, I get x plus 2 and x minus 2. So I know I get x equals 2 and x equals negative 2. And if I solve this one, let's see, I could say 4x squared minus 4 equals 0. Add the 4, divide by 4, x squared equals 1. Don't forget you get two answers when you take that square root, plus and minus 1. So, geez Louise, we've got a lot of factors or solutions here to check. Remember, I'm labeling this f double prime, still describing function f. I'm going to put them in order, so let's go negative 2, negative 1, 0, 1, and 2. All right, now comes the fun part, plugging numbers in. Now remember, guys, you don't care what the number is, you care whether it's positive or negative. So I'm going to start with the positive 4 on this end. Okay, I've got three terms. I'm plugging it in this term, and this term to determine whether I'm positive or negative. All right, so when I plug it in here, 2 times 4 is a positive. Anybody I put in here, I'm squaring. What is every term going to turn out to be here? It's this quantity squared. I'm going to get a positive. And now I have to be careful on this last one. 4 squared is 16 times 4 minus 4 is a positive. Positive, positive, positive is a positive, which tells me that this is concave up. I'm going to plug in a 1.5 or 3 halves. 2 times 3 halves is a positive. This middle term is always positive because I'm squaring it. If I square 3 halves, I get 9 fourths times 4 is 9, minus 4 is a positive. So that's concave up still. Here I'm going to plug in a 1/2. 2 times a half is a positive. The middle term is always positive because we're squaring it. 1/2 squared is 1/4. Times 4 gets me a 1, and 1 minus 4 is a negative. If I multiply those together, I get a negative. So now I'm concave down. Plug in a negative 1/2, I'm going to get a negative times a positive times a negative, which is a positive. This is concave up again. If I plug in a negative 3 halves, I'm going to get a negative times a positive. Again, negative 3 halves squared is 9 fourths times 4 is 9. 9 minus 4 is a positive, so that's a negative when I multiply those. And I'll plug in a negative 4, so that's a negative times a positive times a positive. Gets me a negative, so concave down there. All right, so real quickly, let's sum it up. My intervals of concave down are from negative infinity to negative 2, from negative 2 to 1, and from 0 to 1. How do I know that? F double prime is less than 0. I'm concave up from negative 1 to 0, from 1 to 2, and from 2 to infinity. How do I know that? F double prime is greater than 0. Now again, I just want to be clear, why am I not just saying from 1 to infinity? Well, at 2, remember, you are not concave up or down at that point, all right? So be careful there, okay? That's a critical point. And let's see, points of inflection. All right, do I have any points of inflection? Well, I think I do. Not everybody is. Negative 1 is, because I went from negative to positive, positive to negative, and negative to positive. So I think I have 3. At x equals negative 1, x equals 0, and x equals positive 1. And remember, my justification for points of inflection are f double prime changes signs. Okay, I don't care what signs they change from negative to positive or positive to negative, just the fact that they change signs. All right, consider this next problem. We have a differentiable function f with a given second derivative. Find the x-coordinate of any inflection points, and then state the intervals on which f is concave up and down. So hopefully it's screaming at you on this page. Points of inflection, concave up, concave down. All of that means look at the second derivative. Now what's so generous about this problem is who did they give you? They gave you the second derivative. They did all the calculus for you, and this happens on the AP a lot. Read who you have. Okay, so basically all I have to do is set that second derivative equal to 0 and get my critical points. So I'm really just teeing up each section and setting each piece equal to 0. And getting each of those points. So here I get x equals 0. I can kill that fourth, take the fourth root of 0, and I get x equals 3/2. Here I get x squared equals 9, so don't forget you get x equals plus and minus 3. At this point, I basically just need to create my sign chart. Remember, we're talking about f double prime, and it's always describing function f. That's not changing. Okay, you are always putting f on the bottom, the main function. Stick these in order. I've got -3, I've got 0, 3/2, and positive 3. And remember, this is all where your slope equaled 0. Okay, those are where my derivatives equaled 0. All right, now keep in mind, we don't actually care what number we get. We care whether we get a positive or we get a negative. So I'm going to start with 4 over here. And I'm plugging it back into my second derivative. Basically, I have 3 terms factored. I have this term, and this term. Now, the one special fact is that this middle term, I'm raising it to the 4th, so it's always going to be positive. Remember that. All right, so I've got -2 times 4 cubed is a negative. I'm always going to get a positive for my second term. 4 squared is 16 minus 9, which is a positive. So a negative times a positive is a negative, which tells me f is concave down here. I'm going to use a 2 in this section. -2 times 2 cubed is a negative. Always going to get a positive for that middle section. And let's see, 2 squared is 4 minus 9 is a negative, which gets me a positive concave up here. Keep going, I'm going to use a 1 in this section. -2 times 1 cubed is a negative. That middle section is always positive. And 1 squared is 1 minus 9 is a negative, which gets me a positive concave up. I'm going to use a -1 in this section. So -1 cubed is negative, times a -2 is actually a positive. The next term is always positive because it's to the 4th. And then times a negative, so I get a concave down. And lastly, if I use a -4, I'm going to get a positive times a positive times a positive, which of course is a positive and concave up. So let's just quickly write out those intervals where I'm concave up and justify. So -infinity to -3 and 3/2 to 3. My justification is f double prime is greater than 0. Concave down from -3 to 0. Where else was I? And 3 to infinity. F double prime is greater than 0. And I believe I missed one of my concave up ones. Let's see, I did -infinity to -3, 3/2 to 3, and I think I need to slap in there a 0 to 3/2 as well. Sorry about that. And lastly, any points of inflection. I would say I have several points of inflection. I have one at x equals 3, -3. So that went from positive to negative. I have one at x equals 0, from negative to positive. And lastly, at x equals positive 3. Now remember, for points of inflection, all we're saying is f double prime changed signs. Well, we've got ourselves one last monster problem for the night. And this is, again, it would be a typical AP problem. Notice it just says find any points of inflection. So again, points of inflection talk about the second derivative. Now, they're going to make us work pretty good here because they started us off with just g of x, and we need g double prime. So let's go get g prime. Read it out loud. 2x times that quantity. So let's go product rule. First times the derivative of the second plus the second times the derivative of the first. Okay, this guy's derivative is 3, keep the inside, squared times the derivative of the inside. and then times 2 over here. Before I dare take my second derivative, we're going to clean this puppy up. Otherwise, we're going to create a mess for ourselves. All right, so I'm looking on this side of the plus sign and this side to pull out a GCF. I could pull out a 2 and the quantity 4x minus 1 squared. Okay, and then I'm going to bracket in what's left. So from this side, I took out a 2 and I took out the 4x minus 1 squared. So it looks like I have an x, a 3, and a 4 for a total of 12x. Then we have this plus sign. I took out the 2 and I took out a squared, so I have 4x minus 1. Again, I'm going to clean this up before I dare take that second derivative. I've got 2, 4x minus 1 squared, and this gets me, let's see, that's 16x minus 1. Okay, I'm actually going to go one step further and clean this up. I'm going to say I can multiply this 2 by this junk. So I'm saying g prime of x is actually equal to 4x minus 1 squared times 32x minus 2. Okay. All right, so that's just g prime. I need to go get g double prime. So as I read this, it's this quantity times this quantity. Product rule again. So I'm going first, derivative of the second, plus the second, times the derivative of the first. 2 times 4x minus 1 to the first times 4. All right, GCF on each side of the plus sign. What do they have in common? Well, I'm going to go with a 4x minus 1. And just to the first is what I can pull out of both. And I would say I could also pull out a 4. Okay, so on this side, if I pull out just one of those, let's see, 4 goes into 32 8 times. And I'm left with just one of those, we said, so 4x minus 1. Then I've got this plus sign. I took out the 4, I took out the 4x minus 1, so I've got 2 times that quantity, which is 64x minus 4. Okay, and again, I'm just cleaning up, that's all I'm doing. So I've got g double prime equals 4x minus 1 times 4. And then inside here, 8 times 4 is 32x minus 8 plus 64x minus 4. Still chugging, 4x minus 1 times 4. 32 and 64 make 96x minus 12. 96x minus 12. Okay, at this point, I have my g double prime, remember, and I'm ready to create my sign chart. So I'm just going to tee it up in between each of my factors or multiplied pieces. 4x minus 1 equals 0, 4 equals 0, 96x minus 12 equals 0. I get x equals 1/4, 4 does not equal 0, and x equals 12 over 96. 12 goes into 12 once and into 96 8 times. So I've got my 1/8. At this point, I can create my sign chart for g double prime. So g double prime, that describes g. I'm going to stick on 1/4 and 1/8. Now, picture, if you can't decide who's smaller, of course, picture taking a circular pizza. Can you cut it into 4s? That's a 4th. Can you cut it into 8s? That's an 1/8. An 1/8 is clearly smaller than a 4th. So lastly, I'm just going to test some points between an 1/8 and a 4th. I'm going to pick a 6th. All right, clearly just somebody that falls in between those two. On this side, I can easily pick a 0 to test, and on this side, whoops, wrong way, I can pick a 0 to test here, and on this side, I can pick a 1. So let me remind you, as that denominator gets larger, you get closer and closer to 0. So anyways, we're going to test those points. We're going to plug them into g double prime. Let me just box in g double prime. I am plugging it into this factored version. That's usually easiest for me, and to see what I get. I'm going to go ahead and do my math. I get a negative, negative, positive. I get a positive. See, that turns out to be a negative. This turns out to be a positive. So I have concave up, concave down, concave up. And you can clearly see that we have 2 points of inflection at 1/8. So again, you can abbreviate a POI at x equals 1/8 and x equals 1/4. My justification is that G double prime change signs. Okay, notice I'm not saying positive to negative, negative to positive. I don't care. All I care is that the signs got changed. Well, that does it for us tonight. Have a great night, and we'll see you tomorrow.